Very good morning to you, Partha. Thanks for both you and Vishwesha for inviting me for this wonderful workshop. And before I start speaking about tipping in thermoacoustic systems and their early warning, I want to acknowledge my colleagues and collaborators, Dr. Induja Pavitran, actually she is there, and Dr. Vinit Nair, Dr. Girish Tampi, Dr. Vishnu Unni, Akshay Sheshadri, Anirban Mishra, and Dr. Partha Dutta, who is organizing this. We had written a nice paper together. Also, the kind of work we do needs a lot of money. So I want to thank Department of Science and Technology through their SCRB core grants and JC Bose Fellowship and Sona Jayanti Fellowship for supporting me. Also want to thank my institute for their IOE grant and also Office of Naval Research Global, who have been our big supporters over the last decade or so for funding this kind of work. So let me just plug in my charger. Yeah. So we are seeing critical transitions and tipping. So what is tipping? Tipping, you must have heard several lectures on this, but this is my version. Tipping is the sudden shift in the state of dynamical systems with slight change in system parameters. And tipping is prevalent in natural, social, technological, and economic systems. So you can have a small change in the system parameters, and you can have a very big shift in the state of the system. So examples include Arctic sea melting, epileptic seizures or asthma attacks, spontaneous asthma attacks, collapse of ecosystems. A slight change in the climate can actually lead entire ecosystem to collapse, financial market crashes, etc. Tipping can have dangerous and catastrophic consequences most of the time. So we are primarily concerned with tipping in thermofluid machinery, and tipping or critical transitions occur in thermofluid machinery and are often dangerous and catastrophic. So here I'm showing three movies. First one is the F1 engine, which is the big rocket which took man to moon, exploding during its first static test in 1962. The middle one is a tail undergoing aeroelastic flutter, and the last one is again a flow structure interaction, collapse of the Tacoma Bridge. First, I will speak about the picture that is our leftmost, thermoacoustic instability. So the best way to see thermoacoustic instability is to see the movies. So we will get into a time machine and go back to the mid-20th century when the mankind was trying to go to moon, and there's a picture of the Saturn rocket on the left, and the F1 engine which powered the Saturn rocket. There were 5 of this. That's on the right. And when they tested this engine,
Sonny Morea was project manager in June 1962 when NASA test fires its first F1.
When you tried to fire it for the first time, just blew apart.
As F1 engines keep blowing up, engineers finally identified the problem: combustion instability.
Okay, so these machines are deadly things. They have so much energy density of about 30 to 40 gigawatts per meter cubed, and the entire power consumption of these 5 engines together is more than the power consumption of UK or Germany. So it's that kind of power. And the thing blows up, you can imagine it's disaster. So energy conversion through combustion drives, rocket, aero engines, and gas turbine-based power plants. And combustion instability is a plaguing problem in aero engines and power plants, leading to failure. The shown here is a picture in which the nozzle of a rocket is blown away, and they found it 2 kilometers from the test stand. So this combustion people, rocket people, are very secretive about things, but surprisingly, they give a lot of pictures, except that they won't tell which picture corresponds to which rocket. Okay, but this is an example of this disaster, and what causes it? It's the feedback between the acoustic field, the sound waves, and the flame. And this positive feedback drives large amplitude oscillations that are really catastrophic. And thermoacoustic instability, it's also called combustion instability in the community, leads to catastrophic failure in aero engines and rockets. And it also leads to catastrophic failure in gas turbine-based power plants. It affects the structural integrity of engine, and you can see on the left is a picture of the engine before the onset of instability, and on the right is a picture of the engine after instability happens. So there's a lot of damage. Also, in the case of rockets, the oscillation is so large that it overwhelms the thermal protection system, and thermal protection system can melt. And this is an article from Wall Street Journal, which talked about what happened to gas turbine engines used for producing electric power. So there were in the late 80s, or early 90s, there was this concern about acid rain, that is nitric acid falling along with the rain. And the reason attributed to this was that during combustion, oxides of nitrogen were produced, NO and NO2, the pollutants. And people then wanted combustors that will have very less oxides of nitrogen being produced. So they try to make this technology called lean premix pre-vaporized combustion, where they actually started burning with a lot of excess fuel. But then, and this technology was supposed to solve all the problems with acid rain. But then when they put it to the field, the combustors start to blow up. Actually, you can see very funny things written there, but it's actually very disastrous, and the gas turbine companies nearly went bankrupt at the time. So the direct losses due to thermoacoustic instability exceeds $1 billion annually in industrial gas turbines, and about the rockets and aero engines for military planes, etc. No one tells these figures because they're all covered up under the guise of national security. But there is really a lot of losses, both in terms of lost time and serious loss for money. So the transition from a stable operation to thermoacoustic instability is a critical transition with catastrophic consequences. And first, we will look at transitions in laminar systems. Now, there are both laminar fluid machinery and turbulent fluid machinery. In a laminar system, the flow will be smooth and nice, and turbulent flow will be rough and violent. So that is a gross description. You probably know that they're characterized by something called Reynolds number. So when the velocity is low, Reynolds number will be low. So Reynolds number is density times velocity times a characteristic dimension divided by the viscosity. So we'll first look at transitions in laminar systems, which will look very much like the transitions which you guys are discussing there. So we perform experiments in a very simple experiment because you don't want to deal with rockets and all that in the laboratory because it gets very dangerous. So this is a simple horizontal Ricky tube. There's not even a flame, but we actually provide the heat through electrical heater, and then we measure the sound pressure level using acoustic signal using piezoelectric transducer. So I will not go into the details of it, but we'll get straight to the signals. If you have any questions, you can certainly contact me about the details of the experiment setup. And this is how the picture looks like. And let me get this pointer. Yeah. So these are the electrical leads, and heater is somewhere inside, and this aluminum duct is the duct through which in which the sound field is set up. So I want to ask this question: how close are we to the onset of thermoacoustic instability? So the idea is to check whether we can predict the proximity to thermoacoustic instability using data from stable operation. So as you change the control parameter and run the system, the signal looks like this. So we want to know whether this is going to a dangerous condition, that is a large amplitude limit cycle, or it will not go. So these are limit cycle oscillations actually, because I have taken data for a long time. It looks all black, but if you zoom in, you will see periodic signals. So developing early warning signals for abrupt transitions in real systems is of critical importance. And we know that although there are several different complex systems, dynamics of complex systems close to a critical point have generic properties, even for many different disparate systems. And we use these generic properties like critical slowing down to provide early warning EWS to these transitions. So you might have been discussing all this for a whole week. So we will look at these various measures. I will not go into any detail because it's all done. Root mean square of fluctuations, lag on autocorrelation, variance, skewness, kurtosis, etc. So in this system, you can see that see this is the pressure amplitude. It rises fairly abruptly. The system actually takes finite time the amplitude to grow. And here is the autocorrelation. You can see that it starts changing well before the pressure amplitude starts rising. So this red line corresponds to the time when the amplitude is rising. And for us engineers, we want to know whether something is going to happen much before. Variance pretty much follows the RMS, so it's not giving any early warning per se. Skewness and kurtosis are not giving definite indications, but lag on autocorrelation is working very well consistently. We also tried this out on a noisy Hawk bifurcation model with additive noise, and we can obtain similar results. So autocorrelation is changing well before this rise in pressure amplitude. Other signals are not showing anything well ahead and or either not working clearly. Now we want to look at transitions in turbulent system. So laminar systems are very nice for the laboratory and they give abrupt transitions, but in reality, in real engines of passenger planes or fighter aircrafts or rockets, we actually have turbulent flow, very highly turbulent flow. So it's important to look at it, and that's what the industry cares about. So we will first look at turbulent thermoacoustic system. Afterwards, we will look at general turbulent thermofluid systems towards the end of the talk. First, we will speak about turbulent thermoacoustic systems. So we can think of a turbulent reactive flow field as a complex system. This is a picture of a combustor, one of the combustors that we have. So there is flame, which is turbulent, which is wrinkled and so on, lots of degrees of freedom. There's turbulent flow with lots of degrees of freedom and lots of scales, and there's acoustic field, molecular changes, reaction happening, mixing happening. So it's really lots of subsystems interacting. And you can view thermoacoustic instability in turbulent combustor as order emerging from chaos in complex systems. Now, this is how the actual burner looks like. So there is a duct and very fairly high flow. We have Reynolds number of the order of 20 or 30 times 10 power 4. So 20,000 to 30,000. And we measure the acoustic pressure of the sound using pressure transducers, piezoelectric pressure transducer. We also do a whole bunch of other measurements, but I would not go into that. If you're interested, please contact me. This is how the photograph of the setup looks like. And a zoomed version of that would look like this. And we call it TARA. It's a nice name, Thermo-Acoustic Rig for studying axial mode instabilities. And what is the problem here? Now, we're changing the control parameter. So you are changing Reynolds number here or the airflow rate. And then we are actually measuring. So you can either measure the RMS value of the signals, or we can measure the take the fast Fourier transform FFT and find the peaks. And if you look at these peaks, and industry generally follows this, they take the FFT and look at the peak. And if you see, you don't really know if there's going to be any change or not. If I look at carefully, it looks like it's changing, but then again take a look, maybe it's not changing. And there'll be some change as you increase the Reynolds number, increasing the flow velocity. So the general turbulence level will be increasing. So now I am quite nervous. If I'm an engineer operating it, will I continue to go like this? In this case, there is no danger. But if I get nervous looking at the signal and turn the machine off, then it takes half an hour to turn off the machine, and it takes another half an hour to turn on the machine. So that is not nice. And I don't mind this sound because this is low amplitude aperiodic oscillations, and they don't create any catastrophic damage, but they will slowly induce wear and tear. And maybe 3 or 4 years later, when the warranty of the combustor is over, that will lead the system to actually break down, which is good for me as a manufacturer, because actually manufacturers make more money out of post-warranty repair. So I don't have any problem with this. But my problem is this: if it is going to be, if there is a large amplitude rise suddenly, then I want to know. I want to be able to shut it down well before it came close to here, because when it comes close, it can suddenly tip to a large amplitude system. So this is my $1,000,000 question. Now, if such a thing is happening, and if I don't turn off the machine could get damaged. And so actually, this is danger. Here, if I turn off when it's not going to go, I'll probably get fired because I did wrong decision. If this is happening, maybe my boss will get fired first before I get fired because the machine is damaged. It's, it costs a lot. So I want to know by looking at the first 5, 6, 10 points before nothing happened, that this is okay and this is not okay. So that is the whole idea. So we want to know how close we are to thermoacoustic instability before any serious change happen. And is it a go or a no-go? Can we predict the proximity of the thermoacoustic system to thermoacoustic instability using data from stable operation? So the classical definition of critical transition says that, or generally includes the property that there should be an abrupt change in the state of the system. And such abrupt transitions occur in laminar systems and really not in turbulent systems. I'll illustrate this by showing you signals from turbulent systems. So if you see the signal, on the top most is the stable operation, because turbulent flow is never silent. For example, you can go to a kitchen, a tea shop or canteen, and you can see the flame actually makes sound. So this is the quietest that you can get, and it still gives fluctuations. So we never have a silent state. And then as you increase the operating parameter, eventually it reaches thermoacoustic instability and doesn't abruptly reach. First, it starts bursting. So there's a state of intermittency that happens first. So it starts bursting, and then it bursts, get more and more, and eventually it gets to thermoacoustic instability. So turbulent flows are accompanied by fluctuations, and these are deterministic fluctuations. They are not random fluctuations like adding noise to a system and all that. They are really turbulence. Turbulence is correlated. Turbulence is deterministic. They are described with Navier-Stokes equation. So tipping in the presence of inherent fluctuations may not look like a clean critical transition as would be explained in all the literature on critical transition. But these deterministic fluctuations and the change in their characteristic during the transition can actually be used to our advantage to obtain early warning signal. So this is a very messy situation, and it doesn't jump up abruptly, but it climbs up steeply like a sigmoid. And as an engineer, what I want to know is, well before the amplitude goes up, well before the sigmoid, I want to know that something is going to happen or not, so that I can, they will go over the parameter very rapidly. If you're away from the instability, if you're close to instability, they want to go slowly. So we want to know all these things. And is it possible to exploit this messiness, this turbulence, and determine how close you are to the onset of thermoacoustic instability? So at the case of stable operations, we actually have low amplitude oscillations, and these are aperiodic, and the community calls them combustion noise. Let me play the sound. I have to get this pointer out. Okay. So these are low amplitude aperiodic oscillations. You don't hear a tone. But now, when you have thermoacoustic instability, you can hear actually periodic sound. I'll play the sound. Okay, so this is actually very loud, but here the amount of sound you hear is limited by the capacity of your loudspeakers. Okay, but actually it can get very loud. In the case of the F1 engine, the amplitude of the sound was 100 atmospheres. Can you believe 100 atmospheres? And between chaos and order, we have intermittency. So I'll play the sound, but please watch out. You will see both this aperiodic oscillations, which is like a general background roar kind of thing, and the system will try to burst out every now and then. So you can just listen to the sound. I hope you got an idea about the sound. So the transition is not from a quiet state to limit cycle. We go actually from stable operation, which is characterized by low amplitude aperiodic fluctuations, to oscillatory instability during the unstable operation, which is a periodic signal or limit cycle oscillation. So tipping to oscillatory instabilities in turbulent system follows an intermittency route, and this was discovered by Professors Vineet Nair and Girish Thambi along with me. So, in turbulent systems, using lag on autocorrelation, which is very successful in laminar combustors, can actually be problematic, because lag on autocorrelation can be high even far from tipping, because turbulence is correlated. So you see, this is quite high value to begin with. So you can't really get any idea of from lag on autocorrelation. We also know that the autocorrelation estimated the lag may increase or decrease as we approach the critical transitions. Below a certain time period, it will go one way. After T/4, it will go the other way. So these ideas are described very well in Burry et al. So what we do is to find variance of autocorrelation. That is working brilliantly. So the amplitude starts going up somewhere here. Let me get the pointer again. So somewhere here, the amplitude starts going, but you can see the variance of autocorrelation start rising before the amplitude of pressure starts going up. And that is our key interest, because we want to know well before the amplitude of pressure went up, whether any other measure is changing. Now, are there any other measures to indicate this transition? Now you can ask, why do you need several measures, one measure or two measure, what? Well, we want to avoid or be able to get rid of false positive and false negative. And so we need many measures, and we also probably need a sequence of warnings and so on and so forth. So we resort to non-linear time series analysis, and we will look at fractals. The fractal time series has a self-similar structure with patterns that fill non-integer dimensions. So if you zoom in on this first signal, you will still see something similar to it. If you further zoom in on a small part of that, you still see something similar to it. So the signal during stable operation appears to be self-similar. This is a 2-second data, and I zoom in on the first 1 second, and I can see similar pattern. And if I zoom in again on the first half of it, you will again see similar pattern. So this seems to be self-similar. And to study self-similarity, fractals provide a natural framework. Now, fractals have fractional dimension. And what is this fractional dimension or fractal dimension? So this is answered by Mandelbrot by asking this rhetoric question, how long is the coast of Britain? So the idea is that you try to measure the perimeter of the coast of Britain, and you see that depending on the ruler you use, you get different values. So if you use a big ruler, you can't really measure the small wrinkles. As you shrink the ruler, you will see, you'll trace more and more contours, and then the perimeter will keep increasing. In fact, the perimeter depends on the size of the ruler, and perimeter has a power law relations with the size of the ruler. And if you plot perimeter with a scale or a ruler size on a log plot, you'll get a straight line, and the slope gives the fractal dimension. So this is the fractal dimension of a geometric object. What about the fractal dimension of a time series? So for a fractal, measures of dispersion such as standard deviation will not converge. So we will exploit this property of the fractal to get a measure. So we use MFDFA, which is multi-fractal de-trended fluctuation analysis. Now, why do we do this, and why don't we do the regular, construct the attractor and look for the fractal dimension? We want to do it live. We want to get an answer in quarter second or 1 second or something very rapidly, because now we are dealing with live machinery, which changes in seconds or sub-seconds. So that's why we use MFDFA, which is very fast. So what we do is to plot the RMS of standard deviation versus time scale in a log plot. So there's a power law between these two, RMS of standard deviation versus time scale. So in the log, it will be a straight line, and you will see if you have a sine wave, it's a Euclidean object, so it's not going to have any scaling. If you have white noise, you have a scaling of half. And combustors, when they operate stably, they have this chaotic signal, and it will have a Hurst exponent. It will have a slope between around 0.2, 0.3. The slope is called Hurst exponent, and Hurst exponent quantifies the fractal characteristic of a signal. And Hurst exponent is related to fractal dimension of a time series, as Hurst exponent is 2 minus fractal dimension. So signals are generally classified as persistent and anti-persistent. So this is a picture I've taken from Musicma, which is a company which advises you on which stock to buy. So we have persistent signals and anti-persistent signals. Persistent signal is if the value is going up, a trend of going up is more likely to be continued by a trend of further going up. Or if it's going down, it will continue to go down. Anti-persistent means if it's going up, it's coming back. If it's coming down, it's going up. So this is mean reverting. So A persistent signal will have a Hurst exponent value between 0.5 to 1, whereas an anti-persistent signal would have a Hurst exponent value between 0 and 0.5. And white noise would have 0.5. And a perfectly periodic signal would have a Hurst exponent value of 0. So this signal, this concept of Hurst exponent is used widely in stock markets. Will Hurst exponent work as a precursor for laminar system? We are looking at the complicated turbulent system, but can we check whether it will work for our laminar reiki tube, which we first looked at? So the laminar system, the first 5 plots are already shown. The last plot is a Hurst exponent. Now you can see that this is really working very well, and it changes well before this red line when the amplitude starts going up. So for the laminar system, Hurst exponent works just, and the lag on autocorrelation also works very well. Both of them work very well. So definitely Hurst exponent is indeed a good precursor measure. Now for a turbulent system, the Hurst exponent will smoothly approach 0 as we approach the impending instability. Now we have to pay close attention to the word impending instability, because if you look at the pressure amplitude, so top plot is the pressure versus Reynolds number for a swirl stabilized burner, and the right side plot top is a variation of pressure versus Reynolds number for a bluff body. Now you can see that in the first 3-4 points, there is a very low amplitude signal. Okay, eventually the signal went up, but even in this first 3 or 4 points, the Hurst exponent plummeted, indicating that instability is hiding around the corner. Now on this right column, if you see, the amplitude stayed, this is the first picture that I showed you, almost constant, very nearly constant for about 10 or 15 points. But you can see from this Hurst exponent plot that it is steadily going towards 0, which is saying that it's approaching an impending thermoacoustic instability. So Hurst exponent is a very good measure to detect the proximity of a turbulent system to the onset of periodicity, or what engineers would call stability margin. As we approach an impending instability, we see that the Hurst exponent approaches 0. The one more thing which I'm not going to talk about, but actually the turbulent signals are multifractal, as those of you who know fluid mechanics would know. And this multifractal spectrum will collapse and lose its multifractality. But I will not get into this. I just want to mention this. So we have some papers and patents on this topic. So when you are faced with the question, life and death question, or $1 million question of is it going to go like the left one or the right one? Now we know the answer, because by looking at the Hurst exponent, we know the answer well in advance. We have other measures. As I said, we use a host of measures. One thing that physically happens, if you look at the spectrum keeps rising and it's converging. The spectral width keeps narrowing down. So is there a way to quantify it? We quantify it by taking the products of the second moment and the first moment. Actually, there are many such measures. In this case, I'm going to show one measure which is based on the product of second moment and first moment. And this also gives early warning. But we also use this to estimate the amplitude of impending instability. Now, estimating the amplitude of impending instability is a very important thing, because there are these possibilities. So you imagine this is the signal, same signal I was showing. You could go to a low amplitude instability, and okay, there will be a little bit of shaking and vibrations, but nothing happens. A little bit. You all are in an aeroplane, some turbulence comes, you shake around, but doesn't disagree or anything. But if it's going to large amplitude, then there can be a problem. So what is the amplitude at the onset of instability? Because knowing the amplitude will help in selecting the strategy to deal with instability. Should we ignore this because a low amplitude thing, or is a mega thing? So should we take evasive action? So this is the question that the engineer is facing. So in Dutta Pavitra has shown that there is an inverse square law scaling with Hurst exponent. Its amplitude is proportional to 1 over Hurst exponent squared. And this actually helps in predicting the amplitude. And this is a kind of, it has a universal nature to it, because it works for several different combustors and also the turbulent thermofluid system without combustion, like aero-acoustic or aero-elastic. She also found another scaling law with the moments of the amplitude spectrum, that amplitude proportional to 1 over m power 2/3. And again, with this, you could actually predict the amplitude. How do you predict the amplitude? We take signals during stable operation, then we project this line, and then we know what's the kind of Okay, A is where you get the perfect sine wave, but you don't get perfect sine wave. We know what's the kind of noisy signal you get. And with that, you can estimate what would be the amplitude of the instability which you will encounter if and when it comes. So we can know in advance the amplitude. This is very interesting and very, very helpful for the protecting the engines. So that is, if you once again just illustrate, we have data from stable operation and we go to unstable operation and we get a prediction. This prediction works very well. We have other methods of characterization also. We use, for example, intermittent statistics to obtain the amplitude. I will stop with this for, I'm not going to go any more into it. So, but to perform control actions, because we don't want the system to get into a large amplitude instability and blow up. So we need to have prior knowledge of the proximity to thermoacoustic instability, and we really like to also estimate the amplitude. So the traditional measures used, like I said, RMS or FFTP, they don't change for a while, and this, whereas the EWS measures change well before, actually, really well before. So this is fantastic and very useful to the industry. Now we look at another scheme of measuring things, which is recurrence analysis. So here we use second space, phase space. We construct the phase space reconstruction using Takens embedding theorem. So we take the pressure time series, and now we need to find a time delay. And we find this time delay by plotting the average mutual information versus various delays, and we take the first minima, and then we take the signal and make delayed copies of this. So if we have P of T, we use P prime of T plus tau and P prime of T plus 2 tau. And then we also need to know the number of dimensions. So what we do is keep increasing the dimension, and we keep increasing it till the false crossings come down. And then we construct the phase space. So this is the reconstructed phase space. So imagine the thing on the left is the reconstructed phase space. This is a very nice illustration from my friend Marvin. So you start with a point, and we are checking whether the trajectory will recur there. To recur there, we'll put an epsilon ball and see if it's coming inside. So here the trajectory has recurred, it's inside the epsilon ball. It's like when you run on a stadium, you start from some point and then you run around and come back to the same point. And then you have recurred to some point. So then you put a black dot. And if you didn't recur, that is, it didn't come to close there, you put a white dot. So in the end, you get patterns, and human beings are very good at detecting patterns. So for a limit cycle oscillation, what's on the left, you get evenly spaced diagonal lines. For quasi-periodic signal, we get diagonal segments with unequal spacing, and this is a manifestation of the incommensurate frequencies. And for a intermittent signal, you get a recurrence plot having black patches of squares and rectangles, and we also see some white patches, and you also see, if you look carefully, you'll also see some diagonal lines here and there. So this is the characteristic of intermittency. The diagonal lines corresponds to the periodicity, and the black patches correspond to the signal being stuck in the aperiodic part, low amplitude part. So we can look at the recurrence plot. It will show a pattern, clear pattern, as we transition from low amplitude periodic oscillation, which I call stable operation, to high amplitude limit cycle oscillation, which I would say is unstable operation. So stable, unstable is from an operation point of view. So for this low amplitude signal, you see this is a grainy plot. And for high amplitude signal, you see diagonal lines. And in between, you have this intermittency. So where you see the black patches, diagonal lines, white patches, etc. Okay. And now this is not just a picture, but you can get measures to quantify this recurrence plot. So for example, RR, recurrence rate, indicates the density of black points in this plot. The trapping time indicates how long the signal is stuck in a low amplitude region. And you can see that the pressure amplitude is going up a little bit late, but these measures are varying well before the pressure amplitude started going up. Next, I want to use the concept of complex network, which is a very popular subject these days. So complex network is the ideal way to represent a complex system, because complex system consists of a large number of interacting components and subsystems, and their interaction can be encoded into these edges. So you have nodes which represent the subsystems of the components, and edges that denote the interactions. So we can use lots and lots of algorithms to construct complex network. We can use visibility graph to convert a time series into complex network. What we do is to pick the local peaks. And so here are these peaks, and you can see if I connect, I will connect a peak to something I can see. So that is the visibility. If I can see from this peak, then I'm going to connect. Whereas this peak down here, I cannot see directly, so I'll not connect. So this is the algorithm, as simple as that, ridiculously simple, but it's fantastic. So we will proceed to characterize time series from thermoacoustic systems using complex network and see whether we can get any useful interactions. So if you construct a network and if you plot the fraction of nodes having k number of connections versus k, which is the number of connections. So we can, and then on a log plot, these plots are usually plotted on a log plot. And you will see that log of pk and log of k has a straight line, which means that p of k has a power law relation with k. P of k goes like k power minus gamma. These are called scale-free networks, and the exponent is typically between 2 to 3. And this is our stable operation has a scale-free characteristic. This is very interesting. And we tried this out on several combustors. All of them have scale-free characteristic, and this exponent is between 2 to 3, as has been propounded by Barabasi. Now, what happened during the transition? So the scale-free network will change to a regular network, because when you have a regular network, each of the peak in a sine wave has same amplitude. So every peak can see the neighboring peak, but the neighboring peak is preventing it from seeing a peak which is far away. So every node has 2 connections, and so you will get a regular network with every one of the nodes having 2 connections. So as we go from combustion noise by intermittency to thermoacoustic instability, the network, complex network, changes its characteristic from a scale-free network on one side to a regular network. And we can, of course, have various measures which can capture the transition well in advance. So there are things like clustering coefficient, short path length, diameter of the network efficiency. All of them would actually start changing before the pressure amplitude starts rising. So these different network measures capture the transition well in advance. As I said, there are many different strategies to construct recurrence network. We constructed a recurrence network. This is work of Vedasri Godavarti, and this is the signal corresponding to combustion noise. Then we went to intermittency prior to thermoacoustic instability. This is thermoacoustic instability. Then we go to intermittency just after thermoacoustic instability. So there is intermittency happening after this as the system goes towards blowout. So this is just prior to blowout. And then, of course, this is white noise. So this is a really clear pattern. It's not anything noise or anything. And you can use the measures and actually get precursors to the onset of thermoacoustic instability and blowout. We have published some papers and we have some patents on this. So what about the emergence of oscillatory instabilities in other aeromechanical systems with turbulent flows? Is this a general funda or is it something very specific? So we look at other systems, aero-acoustic, aero-elastic, and these are the systems, but other people have looked at other instabilities like surge and compressors and so on. But I will present our data. We will first look at aero-acoustic system, which is 2 orifices inside a duct, and there is vortex shedding from a orifice, which makes sound, and that is interacting with the sound in the acoustic field in the duct. So a flute is actually an example of aero-acoustic instability. Flute is probably the only critical transition which is pleasant to hear. Every other thing is catastrophic. So we have a feedback between the acoustic wave, acoustic field in the duct and vortex shedding. And this is what leads to aero-acoustic instability. Likewise, we can look at aero-acoustic, aero-elastic system, which is the interaction between the vibrations and the flow. And like I said, the collapse of Tacoma Bridge is an example of this. And you have feedback between the flow and the structure here leading to aero-elastic instability. So if we look at these 3 different systems, on the left column is thermoacoustics, which is shown with green color. Middle column is aeroacoustics, and the right column, middle column with the maroon color. Right, there's a blue color that is aero-elastic. But if you see, all of them have similar pattern. We go from chaos via intermittency, that is the burst emit regions of periodicity to periodic. So this transition route is universal. This is how oscillatory instabilities emerge in turbulent flows through the intermittency route. And as for all these transitions, as we approach an impending instability, we notice that the first exponent goes to zero, be it thermoacoustics or aero-acoustic or aero-elastic or any surge, and there's a collapse in the multifractal spectrum. And the scaling laws and the scaling laws work across all these systems, not just in combustion, they work with all the systems. And some of Hinduja's scaling laws work for randomness in electronic circuits and so on, but I will leave them. Last thing, another transition I want to talk about is flame blower. If you blow a flame, you can go from a situation where there is flame to a situation where there is no flame. So that is another transition, except it is an absorbing transition. I mean, if the flame is gone, then you cannot reignite it. It's gone. There's no comeback. So this is a very, I mean, candle flame blower is innocuous, but this is a very famous Cold War airplane, SR-71 Blackbird, which reconnaissance plane, which can fly at altitude of 28 kilometers, Mach 3.5. So this is flame blower occurring in this aeroplane, where actually you can see the flame is outside the engine. So the flame has to be inside the engine to be able to get thrust. If it's outside, you don't get any thrust. And this is a disaster in real situation because the pilot has to come down. He has to come down to a lower altitude and then attempt reignition. So this happens in a dog fight or something, you are ruined. I mean, even without getting shot, you will die. So these, we have got precursors. This brilliant work by Vishnu. Now he's a professor in IIT Hyderabad. These precursors work for blowout also. So early variation of precursors measures enables better prognosis and analysis of instabilities, rather than what we are used to is just looking at the peak of the FFT or the RMS value. We get a lot more now. And if we have early warning, we engineers know how to make the combustor stable. There's so many tricks and other trade with which you can do, but it takes them time to implement. So if you know that it's coming, we can implement. But these tricks also have their penalty, because if you make the flame long and make the combustor stable, you may increase the NOx production, pollutant production. But if you know that it's coming, then you can temporarily make it stable and then bring it back to operating conditions where you can, it's not so unstable. So there are strategies, but we need time. And this EWS gives us time to implement these strategies in real systems. And so I'm at the end of the talk. So in summary, we go from a stable operation, which is characterized by combustive noise, via intermittency, which is a regime where there's bursts of periodic oscillations, emit regions of periodicity, to full-blown instability. So this is not a direct transition, and there is, it goes through the state, and we are okay with intermittency. And people never knew about it till we actually started looking at it. People were not worried about it because, okay, it's slight change. The actual RMS doesn't go up. You saw it was just staying flat. All those cases are intermittency, but people didn't notice because they were looking only at the RMS value, the FFT peak. So there is small blip, so you just ignore it. But it's actually what is giving us the early warning. So we developed physics-based precursors. And of course, we also worked on many machine learning-based precursors and hybrid precursors. So we use CNN, and also we use neural ODEs and so on. But I'm not discussing that here. But in future, probably the combination of machine learning and physics-based precursors would be what is going to be ruling the next decade, I would guess. And this works very well for industrial data. We have transferred the technology to General Electric. We have also used it for ISRO. We have actually predicted, from the early tests, we predicted the stability characteristic of Chandrayaan lander engine, actually. Hinduja did this work. And we did, we have done this on engine test and rig tests and all that in General Electric, and also in many other companies we have tried out. And you can actually employ this to protect fielded engines of power plants. And for the rockets, etc., you can actually use it as a very good idea of stability margin. So engineers get carried away by the technology. We try our best to reduce NOx, and we try to increase performance, and we can actually get incredible performance. But then, in this excitement, we get carried away, and sometimes we are at the cliff, and then there is a tendency to follow. So what we need is something telling us that there is a stability boundary here, give us a warning so that you don't go. And RMS is not a good warning because it by the time it changes, and it's not that the system doesn't behave every time the same way. The temperature changes, stability characteristic changes. So we want to know live as it happens, where is the stability boundary, and so that you can stand there with peace. If there is a fence there, you can stand there with peace. You can go to the edge of the cliff and enjoy the scenery. Same way. So we have our commercial system, early warning for thermoacoustic instability. This is something which runs on a GUI and it can interface with any of the transducers. And this is run based on many patents, actually. I only described some of the schemes behind it, but there are a lot more underneath it. And we have published a review in the Vishnu and I published a review in EPJST on critical transition and the early warning signals in thermoacoustic systems. I only gave a highlight of this review, but this is a very long review, and it's fairly comprehensive. And also published this quite a bit in this book. Quite a bit of this book deals with early warning signals and precursors and the funda behind the precursors. So I want to appeal to you to say that thermoacoustic systems are great platforms to test out EWS measures and really have high quality experiment data. So you are testing your measures with differential equation, adding noise to it, small noise and all that, but this is real. And in real data, for example, noise may not be small. Turbulent systems, if you look at the pressure you saw, it is like maybe 25–30%, and it's not just quiet at all. Now, if you look at the velocity fluctuation, I didn't show the velocity measurements, but in a solar combustor, for example, the turbulent fluctuations are actually 20 times the mean flow velocities. So it's really a very high level system with very high level of fluctuations. And this is not noise, this is really turbulence. And we have very high quality experimental data. I only shown some type of transition. We have many more transitions. So I would be very interested in collaborating with you all experts. The message I want to tell is, in a messy world, all the things that you have developed, they work very well. So, and we are very happy to work with you together. We have very nice experimental data taken over a decade of with a lot of care. So I come to the end of the talk, and all this work is possible because of my brilliant students. Thank you.
Fantastic lecture. Questions, please. Yeah, feel free to ask any question if you have one.
Yeah, I'm not hearing anything.
Anyone is having any question?
Hi, can you hear me?
Yes.
Hi, this is Vishu. Thanks, that was a very nice talk. So I have a question about the Hurst exponent you mentioned.
Yes.
Is there any analytical relationship between the Hurst exponent and, let's say, the linear instability analysis? Do we, that connection was not necessarily clear to me. But I understand the idea of the randomness and the features behind it.
Yeah, I don't think there is anything you can do with linear analysis. This whole thing is, whole thing is turbulence. So I don't know if anything linear would make any sense whatsoever. But there is a relationship in Hurst for this financial type of time series. There's actually a relationship between Hurst exponent and the spectra, but those relationships don't work very well for our things because there the spectra is kind of 1 over f kind, 1 over f power alpha kind of spectra. So then you could actually make a relationship. But our system is made, so that's quite used in stock market and so on. But our system is quite messed up because if you have a flame in the open, you would have this declining spectra, f power minus alpha. But we are inside a duct. So the duct modes are going to pop up some of the frequencies. So in the sense, it's a completely messed up signal. So I am not very hopeful that any simple relation can be derived between the spectra and the Hurst exponent. But for an open flame, you can, but open flame doesn't have thermoacoustic instability. There's no feedback and so on. So at the moment, at least I'm not aware of any connection to linear stability and so on.
Okay, thank you.
But it's purely a
That makes
fractal
sense.
measure.
Yeah, makes sense. So I have a follow-up question, if you don't mind. So they showed a very nice linear relationship, right? The Hurst exponent that linearly decayed as you towards zero as you
Right.
went near the instability.
Right.
So can that, and if that is a sort of universal feature across at least certain model cases and systems, so can that be used to identify the distance to the critical point? Because
Yes, actually, absolutely. I think I don't know how to go back to slide just a second. So there are some scaling laws. I'll try to get that. So the scaling laws, and also this, yeah, I mean, we can estimate, I mean, need not always be linear. For this particular combustor on the right side, we had a linear, and for the left one, it had more like a power law kind of variant. So it depends on the class of combustor, but so Hurst exponent versus parameter will have a monotonic relationship. So given that there's monotonic relationship, and for each class of combustor, there's a type of monotonic relationship, we can estimate when it goes to instability. And the amplitude can be estimated from these scaling laws of Induja. So this is a beautiful scaling law, amplitude proportional to 1 over h squared. I never thought, when we got this, we were really shocked that we never thought, we thought inverse square law, etc. are in the time of Newton, but we got beautiful scaling laws. So these are universal. Any combustor, any turbulent system, order emerging, oscillating instability emerging, follow the scaling laws. But the actual variation with parameter, for a given combustor, it shows a monotonic trend, but that changes. But no matter how it changes, this law is held. Did I answer your question?
Yes. Thank you very much. Thanks a lot.
I would be very happy to talk to you directly. I'm sure you guys can do. Maybe the analytical things are not there because no one has tried it. So it's quite possible that you may be able to derive analytical things.
But you're also, turbulent systems are really hard to deal anything analytically. So, but these scaling laws are really interesting.
Yeah.
Thank you.
Thanks.
So there is another question for you, sir, please.
Yes, please.
Sir, in this Hurst exponent calculation, you said you find the qth order fluctuations where you set the q equal to 2, I guess.
Right.
Yeah. So can we change, like, what does this q actually determine, and how can we vary the range of this parameter?
This is absolutely a brilliant question. You can change q from, depending on how good your data is, -2 to 2 or -5 to 5. And then the positive value of q will zoom in on the large amplitude fluctuations. So if you have a value like 10 and you put q as 2, it makes it 100, so it will be positive. But whereas q is negative, will suppress the large fluctuations, but negative q will amplify small fluctuations. So if you have a value of 0.1, 0.1 power -2 will become 100, right? So you can change. So q is like a filter. If you use large q, you're actually zooming in on the large amplitude fluctuation. If you use a negative q, you're zooming in on this small amplitude. So you can use any q, and all of them give similar trend. But we also can get this multifractal spectrum. By that's by looking at various q's. Now the multifractal spectrum collapses, its width decreases and all that. But we are sitting on fire on the backside, so we want to get the calculation very fast and reliable. So purely from that point of view, second order Hurst exponent is very good. But I mean, the multifractal spectrum collapses. Any qth order thing will do this. So purely from a scientific point of view, you are absolutely right. All of them work very well, and we can actually characterize with the collapse of multifractality. So absolutely right. And we use MFDFA, but in the nonlinear dynamics community in India, I know the popular way is to embed and look at the dimension of the attractor. That's also fine, but it takes time to calculate.
And one more thing, sir. Is there anything analogous to Hurst exponent? Because when we calculate the Hurst exponent, we use the temporal data. And is there anything analogous to the Hurst exponent if we have some spatial data?
Absolutely. So that is the fractal dimension. Now, can I take 2 minutes to explain, Partha? If so, okay. So when you have thermoacoustic instability, you have collapse of the multifractal spectrum. So you can calculate the spatial multifractal spectrum, and the spatial field is turbulent, the flame is wrinkled, it's highly wrinkled, but actually it turns out that you can calculate this multifractal spectrum for the space, and then this multifractal spectrum is oscillating periodically. That's very interesting. So you can actually get multifractal spectrum for the space. So therefore, just the same way they would calculate multifractal spectrum of the cities to find out how the cities are, how the population is living in the cities. The same codes you can use, and you can calculate the multifractal spectrum. So Qth order Hurst exponent is what you use, except the algorithms change because you can either so you can detect the edges and calculate. So what we do is to detect the flame edges and calculate the multifractal algorithm, fractal spectrum with that algorithm. But you can also look at the intensity values and get the algorithms with work with that. Like, so you have a 2D space and 3D is the intensity value, and the medical field, they use that. And that's how, for example, to detect tumor and so on. So the various algorithms, you have to choose the one that works well for them. So spatial also, you can absolutely use it.
So thank you, sir.
You can actually detect critical regions, etc. in space. We have some patents based on that to find which regions to control and so on. But it's a brilliant question. Thank you.
Anyone is having any other question? Yeah. So if there is no more questions, sir, I have one question.
Yes, sir.
So we apply these early warning signals based on our simulation data, right? And you do it from experimental data. So I believe that you see much more than that we see. So this theory that this critical slowing down based early warning signal, they should work, because if we do some stochastic calculus, then we see that they will work in weak noise limit. Okay, right. And it theory says that as lambda approaches 0, variance should hit infinity, and the lag on autocorrelation should hit 1. But the analysis, early warning signal analysis that we do, we never give importance to that, the scale of y-axis, right? So how much increase is there? Things, the questions like that. So my question is that, so from your experimental data, do you see something like that happening, let's say in the vicinity of the tipping point, the autocorrelation is really near to 1, or so my basic question is that how much importance we should give to that, to the range in that we see in the Y scale? Right. So in experiments, it doesn't, as you yourself point out, is not the straight analog system. So if you use autocorrelation, it's a turbulent system, so it does so many lags. Which lag do you use? And there's no clear answer. So what Induja did is a brilliant thing. It calculated for all lags and took standard deviation, and that got to work. So the key is you have tools, and how to get these tools work for my system. So that is the way I would rephrase it. And one thing I don't see in the EWS literature is, I mean, I have a transition and it's for real. Now, and I have one system here, another system there. And then in between, I get this intermittency, which is real. I can go to the lab and I can listen. Even when the RMS is not showing anything, I can make out this burst, although it doesn't reflect in the RMS. So that thing, I don't see anywhere in the EWS literature, and it's for real. And of course, I have not looked at all transition, but you only looked at transition to oscillatory instability. So that is something which I do not see in EWS literature. But otherwise, but all your tools are working now. Is there critical slowing down? I don't know, because you are not having a, I mean, it's, you have chaos and you have a lot of unstable periodic orbits, and system is jumping from one periodic orbit to another periodic orbit. So even if there is critical slowing down, again, it depends on the lag which you use to quantify. So it's hard to see, but we are able to make your tools work in some way or the other. And the I think another tool which we use very successfully is the Hurst exponent, which is looking at the
fractal nature of the signal. So systems are not noisy, they are turbulent and they are deterministic, and these things are working very well. Now, as to are they stochastic or not, they are turbulent, and we have shown that they are deterministic noise with little bit of, I mean, there's noise, but the signal is strongly deterministic. But all the tools which are established with the help of stochastic theory are working here. So, I mean, it's working. I mean, I would have thought that many of these things don't work, but they're working, and they're working. And now the one question that the engineers in these companies had is that whether these things will work in industry, because I use Reynolds number of 10 power 4, 20,000. They have 2 lakh Reynolds number, okay? One order more, 10 power 5. And their fluctuations are much higher. But these things work beautifully, because the more the fluctuations, the thing works much better actually. So the chance of catching these things are even better than in the real industrial system. So fluctuations, I love fluctuations. I have to probably make a t-shirt and say I love fluctuations or something. It's working very well. Does that answer your question, Partha?
Yes, yes, yes. Thank you. Thank you. Any more question from anyone?
Like I said, if any of you want to work together with us, we'd be very happy. And we have lots of data. Partha, we have much more data than the time we wrote the paper. So we would be, maybe we should get back together.
Thank you, sir. Thank you.
Yeah, spatial data also.
So if there is no more question, then let us thank again Professor Sujith for this wonderful talk. And we all will be able to meet with him next week when he is here. Thank you, sir. Thank you very much.
Thank you.